All right, how can the rate of a reaction be calculated from a graph? So if they give you this graphing model on the IB exam, what do? All right, very simple. No, you're not going to freak out. All right, the gradient of the graph is equal to the initial rate of the reaction at that time. So we take the rate of reaction equals y over x. And we go up to a certain point. You check it out. Rate of reaction, okay, so we got 45 centimeters divided by 20 seconds. The rate of the reaction is 2.25 cubic centimeters per second. Okay, I don't think that's as, I think everybody in here has done that since 7th grade. Yes?
Does it matter if we're on the line?
No, it doesn't matter anywhere on the line. It does not matter. All right, reactions do not, now there you have a top line that you have to fill in a lot. They start off at a certain speed, then get slower and slower until they stop. That would be equivalent to the plateau on the graph, the plateau or the lowest elevation that stays the same, the rate stays constant. As the reaction progresses, the concentration of reactant decreases. This reduces the frequency of collisions between particles, and so the reaction slows down. Take a look at my wonderful handy-dandy drawing. So take a look. So we had some blue and red. They collide together. So let me ask you this. Let's take a look at this in a little more detail here. Okay. Let's break this down. What are the red and blue balls? What do we call the red and blue balls here? What do we call these things? More specific. Hey, calculator. I got a 6 molar and I got a 3 molar. Yeah, go ahead.
That's what I need.
6 is in here, 3 is in 6. Yeah. All right, what are these red balls and blue balls, Louis? What do you think? Yeah, I don't know what that. I don't know what they are.
I think I know what they are.
What do you think? I got red, blue. Then all of a sudden I got some purple appearing.
Wild guess.
That wild guess. What have we been talking about the whole day?
A.
What's that? Yours are not colored, so just shade them in so you know the difference. Is there one a light and one a dark? Yeah.
The same shadow. Except the purple and the
All right. Well, what do you think here? What do you think these possibly could be?
Yeah.
These are the reactants. Oh my God! Thank
You
you.
said rather. React.
Oh my God! Yes, the reactants. So all of a sudden, so we have. Let's just do this. Watch this. This is going to be awesome. So I'm going to take this and let's see if this makes sense to you. All right. So here we go. I got this. Watch this. Look at that. See that? Now somebody tell me what I did here. Whoa.
Concentration.
Oh, the concentration of red balls versus the concentration of blue balls. All right, so we got those. So this is the first box. And then all of a sudden, when we get to the second box, we have red balls, blue balls, and now some purple balls. All right, what do you think the purple balls would be? The product. All right, so what happened in our graph right now? So we're looking at our graph, and let's just say we had this. So at this point, let's see, our reactants would be like this, and our products would be like that, right? And then also they're going to keep going and keep going and keep going, right? So all the graphs that we went over earlier are leading up to this slide. So as we go across, what's happening? The products are getting more, and what happened to the reactants?
Less.
It's not hard, right? Not hard. All right, but that's a nice visual for you to see that. All right, so then I have reactants and products. Okay, hopefully I didn't really want to reinvent the wheel. It was right here on the slide.
Oh. Well, I mean, we didn't. Just on our slide.
Yeah, it's on your slide.
Yeah.
Percent completion of the reaction. All right, so percentage completion of the reaction. So as we go left to right, percentage completion. All right, next. Consider the hypothetical aqueous reaction between the A, aqueous, whatever reactant we have, and B, the product. All right, so we had this. We have a 100 milliliter flask. Initially contains 0.065 moles of A and 0 moles of B. All right, so moles of A and moles of B. We don't have the moles of B column yet. We're probably going to add that on the next slide. The following data was collected. So we have time and we have moles of A, 0.065. All right, and that's decreasing, which is great. So what are we going to have to do? Yes.
We're going to have to take the moles of A number and then
Yep, go ahead.
and subtract that from 0.065. That difference should give you the moles of B.
Oh, okay, yeah. So it should give you subtracted 2. Well, what do we got? So we have this right here. All right, so it's very simple. I understand what you're saying. So let's see. I have 0 of B here, so moles of B. This is not going to be perfectly neat. How many total moles did I start with? This is the total. All right, it cannot change. It can only transform itself. It cannot change the total amount. So, well, how many moles do I have to have here then? So I'm going to go 0.65 minus 0.051. Okay, that's 0.014 moles of B. All right, understand how I did that? That's not that hard. Yeah. Yes?
Why did you start with the 100 milliliters again?
We'll go over that in a second because we're going to have to do it down here. All right, so now let me see. Let me put this chart up for you. Here we go. Take a look. All right, so here we go. As we did, calculate the number of moles of B at each time in the table. So on the next slide, I gave you room to create your table. If you wrote it on the other slide, that's fine. All right, doesn't matter. Does everybody have, that makes complete sense. There shouldn't be anything there that should be confusing anyone. You had the total amount, and the total amount must be 0.65 in every one. So I'm just going to do my quick little silly math. If I add this up, 0.065, okay, yes. So let me add these up. I got a 5, got a 6, okay, good, I got the, all right, let me leave the 5, I got a 6, I carry the 1. Okay, yeah, all right. Then I got 0.06, yeah, all right. So I added all those up. It's pretty simple. That's not hard. But that's something IB would expect to be able to do, so I figured I had to show it to you because when we hear it once, you should be good to go. All right. Next, all right, graph the change in amount of A and B over time. I went ahead and put it up here for you. I gave you a slide to do it. It shouldn't be hard. I actually used a little bit of an Excel to do mine. So it was very simple for me. So if you notice, then we're going to plateau. Probably these lines are going to continue very close to each other. So all I did was plot. I think everybody's going to have trouble doing that.
I have no idea how to use it. Me neither. My computer teacher in elementary school, she like showed it to her, like she's like, here's Excel, have at it. And I was like,
Okay.
You know about Excel until
Well, like making a table in Excel is really easy, but it's hard, like graphs confuse me.
I don't see the point of making a table in Excel when you just do that word and have.
Yeah, but the table in Excel is so much quicker. Yeah.
Pretty easy on this. Anybody have any questions? You need to leave this up any longer?
Yes.
All right.
I did it wrong.
Is it matching up with everything that we have done so far today? As I said, redundancy in this PowerPoint. Redundancy sometimes leads to better grades on tests. We all need a good grade in our chapter 6.
Yeah, we do.
I haven't really looked at grades, but like after labs.
You might not want to look at
What's that?
mine. You might not want to look at mine.
Don't want to look at yours? Okay. No. It's what it is. You don't have to match the lines exactly, just draw two lines there. All right. Very good. All right, calculate the average disappearance over time. Let me get my reveal. Can't do that. Now I don't want to give it all to you right away. All right, so we have this. All right, so calculate the average disappearance of A for each 10-minute interval. All right, in terms of mole per second. All right, so now I'm going to need some help. I need somebody to tell me what equation we're going to use. What equation are we going to use? Yes?
We are going to do delta open bracket A close bracket divided by delta TS.
All right, T? TS, so I'm going to put TS.
Well, I was still not sure if it would ask for like second or T for time.
T's fine, T's fine. All right, is it positive or negative?
Oh, it's negative.
Negative, all right, so we need a negative here. All right, so again, remember that this is going to be T final minus T initial, or however you want to do that. And the top is not that way, it's initial minus final. All right, so this is concentration at O minus concentration at T equals 10. All right, so see if you can get a number. Tell me what you get. See if you can get a number.
You should have been in the top show.
Oh, I know.
You could have been the MC.
I could have been called Sir Mix-a-Lot.
What?
Sir Mix-a-Lot.
Point
That's
oh
not
oh
what.
What'd you get?
point oh oh 14.
0.0014. How many people agree with that? Uh-oh. Didn't hear a lot of people agreeing with that.
Did you convert it to
No, I didn't.
Anybody else have an answer? No, luckily I do.
Oh, that is what I thought.
Did you get that?
Yeah.
Good. Good. Yeah, you must convert that to seconds because it says moles per second. All right, then it wants you to do, let's see, each 10-minute interval. So you got to do 2 more just to make sure you do it right. Again, one more time, let me explain why did we do this? Why do I have, okay, wow. There we go. Let's see your homework. All right, homework.